So today I'll give a brief introduction to zigzag persistence, and then we'll talk about installing Dionysies on a Mac. The motivation for much of my lecture is Gunnar Carlson's lecture 14 at the IMA videos from 2009. I also stole some slides from Vin De Silva, so he is the one who gave this lecture in 2009 as well, and the slides are posted on this page, meaning I could steal a few of them. So, just to remind you some motivation for the zigzag persistence. Remember when we took a look at the application of image data? Instead of taking a look at all the pixels, we'll instead look at, oops, I forgot to switch the pen. We'll instead look at these 3x3 patches, so all the 3x3 patches. So we had a vector in R9 based upon the gray value here, but then did a few projections, so got the mean intensity to be 0 and the divided by the D norm, so it now lived on a 7-dimensional sphere. So those were our data points. And then when looking at all the data points, you basically saw S7 covered, but it wasn't all evenly covered. There were points that were, there were parts on S7 that were more dense than others. And so this co-density filter was used where the definition of dense depended upon this distance right here, where the distance was the distance from X to its kth nearest neighbor. So again, if we have 1 point, delta 1 would be the distance to the first nearest neighbor, delta 2 would be the distance to the second, delta 3 distance to the third. And so depending upon your choice of K, you have different definitions of density, but we would then take the T% densest points. So if this thing is small, we know that X is dense. We took the T% densest points. So we have mk of t, so we've got those points in the 7-dimensional sphere, but then we use a definition of density, and then we take the T% most densest points. Any questions about this codensity? Does everybody remember it? So they then found a Klein bottle. One of the things in order to find the Klein bottle, however, is they did actually have to add a few more points. So they took the 10% most densest points when K was 100, but then they threw in 30 additional points in order to actually get the persistent homology of the Klein bottle. So some of these points here are not as dense as the others, but they found these extra 30 points that if they threw them in, so these are 30 points that were in the image data, they just weren't as dense, but throwing them in filled out this nice Klein bottle. If you want to see how they chose those 30 points, you can read on the local behavior of spaces of natural images by Gunnar Carlson et al. But I'm just going to be using this to motivate zigzag homology. Any questions so far? So we did have before multidimensional homology, so we could go ahead and take a look at changing T. So maybe I'll take the 10% most densest points or the 20%. Well, the 20% most dense points will be contained in the 10% most dense points. And so we do have all these nice inclusions right here for a fixed K and letting T increase. But that means that we would also have multidimensional persistence, because not only can we increase our t, taking our t most densest points, we could also change our epsilon as well in terms of deciding when to connect 2 points and then creating our RIPS complex. So choosing our epsilon balls to determine when they intersect and then creating the RIPS complex. So we had 2 variables and thus looked at multidimensional persistence. We did take a look at another picture from this paper here with a different multidimensional choice, where in one dimension the radius was changed, so we increased the epsilon balls, and so more and more things were joined together. But in this example, the other variable is curvature. So whatever your 2 or 3 or 5 variables are, we can do this multidimensional persistence. And we saw before the workshops that that made sense, because we could just go ahead and, if we have multidimensional persistence, I can have one direction being represented by the x1 variable, the other direction being represented by the x2 variable, and so I can keep track of when things entered in. So F, E, C, and B all entered in when x1 is 0 and x2 is 0, so x1 to the 0 times x2 to the 0 is 1. E entered in at time x1 equals to 1, x2 equals to 0. And if we take a look at when A enters in, it entered in at x1 equal to 1 and x2 equal to 1. So you can keep track of the time everything enters in, be it a vertex or an edge. Divide the 2 to keep track of the difference between when it enters in and when it might be killed. And then we did our column operations to go ahead and put it into column echelon form. And then we're able to do the notation to say, for example, if I focus on the generator A, remember the generator A came in at time 1, 1 in persistence. I want to record its birth. So to record its birth, we use this shifting notation. And so that just told us that it was born at time 1, 1. But then, so it was born at time 1, 1, not 0, 0 or 0, 1 or anything else. This is when it was born. And then we also needed to keep track of when it gets killed. And it got killed x2 units later. x2 is the vertical direction, so if I go up exactly 1 unit, then we can see that we can kill off A with this edge here, AB, and so we denote that we've killed it off over here. It could also be that maybe I would have killed it off, going in this direction here as well. Now, in this example, we didn't, but maybe I might have also killed it off going the other direction too, in a different one. And if I killed it off 2 units later in the x1 direction, well, then I would have had a second generator when I mod out by. So I'd be modding out by both x2 if I kill it off in the vertical direction, as well as if I kill it off in the horizontal direction 2 units later, I've got x1 squared. So we have this nice notation. Okay, some of you may not think it quite so nice, but if you think about it, it is nice shorthand notation, well, for saying when a generator is born, as well as we mod out when it dies. And so that was our multidimensional persistence. So notation for birth as well as death. Any questions about that? So we also want to take a look at another type of persistence. If, correction. So if I now fix t, so t is now fixed, and I now change k. Well, I'm now changing my definition of what it means to be dense. If I take the 20% most dense points, then I'm taking the same number of points. So this has the same number of points as this, has the same number of points as this. It might look like these might be including in because, this looks smaller than that, but no, it's just these points here are just more dense only along here when K is 500, but I'm still taking the 20% most dense points. So this is not included in here. This is not included within here. They all have the same number of points, but there's no inclusion. So all we've done is we've changed our definition of density. So depending upon how large our K is, we sort of smooth out the data a bit more. So if our K is smaller, we're only looking close by. If K is larger, we're looking further away. We've changed our definition of density. So depending upon our definition of density, our 20% most dense points will be different, but they won't be including within each other. We still have the same number of points. Any questions there? The question is, there is a question, how do we handle this? Well, one way to handle this is zigzag diagrams. We want to compare, for example, so we might want to compare this one here to this one here. Well, there's two ways to compare it. I can take a look at x0, and I can take a look at x1. And remember, we always would like inclusion if we can get it, because then we can talk about things persisting. If we've got an inclusion map or some map, then we can say, does it persist? Does our cycle persist within this inclusion, within these maps? And so we can look to see how things include into the union. So we can look to see how things include into the union. And so what we get is this zigzag, this sort of zigzag diagram where our arrows are pointing, in a bit of a weird way. Now, in addition to union, we could have instead done intersection. So suppose I did intersection here. Well, then I would have just been changing my arrows to go the other direction. So I could have instead having a zigzag persistence like that. But everything works nicely via torus. We won't get into that, but one can easily do either stuff. There's another important application of zigzag persistence. So any questions first upon this application of zigzag persistence? Unions or intersections of sets that may or may not be related to each other. Our witness complexes is also a very interesting application. Remember, quite often it's computationally too difficult to take all the points. So instead we took a subset. So our xi's are a collection of witnesses that we took within X. And then we took a look at cycles here that were generated if they were close to points in X. And so we chose these witnesses, and so our data points, our vertices were just these various different xi's. We connected them depending upon whether or not they were close to X. That was our witness complexes. But we could take different witnesses. So I could take an xi, or I could take an xj, and it'd be nice to compare the two witnesses. And well, in this case, my red witness and my black witness, they both describe the same whole. So when I include the cycles into the union right here, they include to the same cycle, and so that says that our witness is very stable. It's a good witness, so the cycle is meaningful. We can find it no matter which witness complex, whether we use the witness complex xj or the witness complex created from xi. So witness complexes is another place where we again get the zigzag where our arrows are pointing in opposite directions. Of course, I could also take the intersection instead and have my arrows going the other way 2, we can also do that zigzag persistence. So this is an important application. And we can see another type of possibility that we might get for the witness complex. And this really does illustrate what our zigzag persistence means. If now my black generator is this one and my red generator is this one, well, when they include, one generator includes to one thing, the other generator includes to something different. So they include to, cycles that are different. They're not the same. And so that means that maybe this cycle is just because I took this particular witness, maybe it's not quite as interesting. It didn't persist over my various choices of witnesses. So we would say that this cycle might be more meaningful than these cycles. And so this can be used to determine whether or not you've got a good choice of witness complexes and what your cycles mean in terms of your witness complex. Any questions there? There's one additional application of persistence, zigzag persistence, and that is when we use time-varying data. So maybe we have a data set, that at time 0 might be the 3 points, and then at time 1, maybe these 3 points, get really close, and then maybe at time 2, they do other types of things. And so we might have different, and maybe we might even have more points at different times. So we can take a look at data points and where and when they exist at different times. So you can think about time series data. So you might look at some signal processing type stuff and want to see how the signals vary with respect to time. So anything where your data varies with respect to time, you might be interested in understanding how that data works. So taking a look at how that data works, we can also do a persistent homology here. In this case, I took the intersection so I can think about having time going from T0 to, in this case, T4, and I might partition my time into various different segments, and then I might look at the homology associated. I might look at the data points I might look at all the data points between T0 and T2. So I may take a look at all of these data points over here. And then I might take a look at the data points from T1 to T3. And then I can take a look at the zigzag persistence to see how the data points from here vary with respect to the data points from here by taking a look at how they work on the intersection. So I've got this zigzag persistence where this includes into both of these here. So again, I have my zigzag persistence. So any questions about these applications? There's lots of places where zigzag persistence can show up. The different densities chose different points that may not be related to each other. The witness complexes and the time-varying stuff did give us some interesting examples. There is a bit of a difference between these 3 examples, though. In the time-varying data, it's, you probably want to go in terms of increasing time. So with respect to increasing time, it made sense as to how I exactly ordered my data points, that I went, that I did this one before this one, this one before this one before this one. Yeah, these may not include into each other, but I can go into the intersection. When I took a look at here, it also made sense to go in a particular direction. It also made sense to go in a particular direction because I was increasing k. So I was increasing k, and so x0 came before x1, came before x2. Even though they don't include into each other, it was clear what to label x0 and what to label x1. In terms of your witness complexes, though, there is a bit of a difference in that it may not be obvious how to label xi and how to label xj. So there is a bit of a difference in terms of these witness complexes. Which witness do you want to come first? Which witness do you decide to come before the other one? So that would be a bit of a question there. But we do have various different persistent diagrams. We had our multidimensional persistent that we looked at where we did have inclusion. So we're assuming the arrows mean we have some kind of map, including, wherever an arrow points up includes this into this. And again, it doesn't have to be the inclusion map, but that's the only applications we're looking at is where this includes into that. But we have a map into this. And as long as we do that, then we can have a map, at time 0, 0 into, the homology of time 0, 0 into the homology at time 0, 1. So as long as we've got this arrow right here, then we can also use that to induce a map on their homologies. And so this was the multidimensional persistence that we looked at over here. We also looked at the standard persistence. Maybe we'll look at the dual, reversing the arrows. And then we can also take a look at zigzag, or maybe we can take a look at more, general things. So maybe we'll have something, like that. So one could look at all sorts of things, and basically as long as you have a directed graph, you could try to understand something in terms of the persistence homology. So we frequently think about zigzag persistence and other types of persistence as graphs where our arrows, directed graphs where our arrows are the directed edges, and our sets here are our vertices. Any questions over there? So we know the first step to calculate persistence. We take our data points. So we've got our data points, whatever they happen to be from, whether they're from time-varying data or whether they're from witness complexes or changing our density function, however our zigzag came in from. We've got our data points. We know our first step is to create a simplicial complex. So we went ahead and created a simplicial complex. We are going to fix epsilon. So today we will fix epsilon and calculate the Vietoris Rips or the check complex or the alpha shape, whichever one you prefer to do. We usually do our Rips complex. And so we can then go ahead and create simplicial complexes. So our data points just create our simplicial complexes just like we did before. So we've got these simplicial complexes, which we can represent. Remember, we use superscript. Eventually, we will talk about cohomology, but we're not doing cohomology. This is just our time. So at time 0, well, with the time varying, this notation can be a little bit confusing in that time 0 actually corresponds to the interval from t0 to t2. Time 1 corresponds to the interval between t1 to t3. Oops, sorry. Time 2 corresponds to the interval from t1 to t3. Versus C1 corresponds to the interval. So let me, So time 1 corresponds to the interval from T1 to T2. Time 3 corresponds to the interval from T2 to T3. And time 4, the superscript 4, maybe I shouldn't use the word time, but it corresponds to the interval from time 2 to time 4. But we get these simplicial complexes, and C is a lot easier to write then all of this. So C is a lot easier to write than all of this. So we will frequently use the C to denote that we have a simplicial complex. And we can see that we've got this zigzag diagram right here. Well, if we have a zigzag diagram, if we have complexes with inclusion maps, then they are going to induce inclusion maps on their homology. Now, do remember in terms of this notation, what I'm really talking about is a whole bunch of simplices, so linear combinations of I simplices, so I chains, a linear combination of I-dimensional simplices at time 3. And so similarly, my H3 is going to be a direct sum of the homologies, all the I-dimensional homologies, so H0 plus H1 plus H2 at time 3. So remember, this is shorthand notation for taking a look at all the simplices of all the dimension, and this we're using a shorthand notation for all the homologies of all the various different dimensions. Questions on the notation? But if we do have an arrow among the simplicial complexes, that does induce a map on the nice homologies. So just to compare our persistent homology to our zigzag homology, we had our simplicial complex at time 0, our simplicial complex at time 1. So we could take a look at the cycles at time 0 and take a look at those cycles that exist at time 1 and that either exist or get killed off by a boundary at time 1. So that is the map that it induces. We just take a look at all these cycles at time 0, and then we can see where the cycle goes. It'll either still be a cycle at time 1, or it will be killed off by a boundary. So we might have a cycle that remains a cycle, or we might have a cycle that goes to something where now we have that it's a boundary of something. And so we had our persistent homology, we had these inclusion maps on our simplicial complex, so that gave us an induced map on the homologies. And then we could talk about the persistence, jumping, if P is 2, I could go from H0 to H2 by the composition of these two maps and talk about this persistence here. We don't really have the composition down here so much, so with our, with our zigzag homology, it's going to be a little hard to compose these two, so we're just not going to do that. But I can still talk about, since these cycles, since these chains include into these chains, that means a cycle will go to either a cycle, well, it'll go to a cycle will go to a cycle, but it might be killed off by a boundary, or maybe it's not killed off by a boundary. So we still have that a map on the simplicial complex induces a map on the homology. So even with the zigzag, any questions there? So what can we do with these maps? We'd like to be able to understand these maps. So let's just look at some possibilities of types of maps we could have. Assuming we have Z2 coefficients, so just 0 or 1, some possible examples of maps, we'll take a look at this first one first, is I might have that, maybe I have that this thing is Z2 and it goes to Z2, so maybe that's what I have. And then either I've got two choices here, either this is the identity map or everything goes to 0. I could also have the map where Z2 goes to 0. I could also have had a map where 0 goes to Z2 or 0 goes to 0. You know, those are if I'm doing Z2 coefficients, and I only have, right now I'm assuming one copy of Z2 in here. These are some possibilities. If I assume one copy of Z2, I could potentially have this as well. That's another possibility. Another thing one could do is we could take the direct sum or the direct product. We're doing nice abelian groups, so it doesn't matter which. Just think about the cross product. We now have 2 copies. So I now have 2 copies of this thing here. But the nice thing about it being the direct sum or the product, we are actually taking the product of these 2. So if it's the product of these 2, then I know what's happening in terms of these things. So let's say that this one came from here and came from here versus this one came from this one right here. That means, and we'll assume we have the identity map here, and we obviously have the 0 map here and the 0 map here. And let's put the identity map in right here. Well, that means I know what the map is over here. So if I take the product of 2 of these diagrams at the homology level, then I know what an element does here. If I take an element, say, x comma y, well, in this direction, it is the identity map on the first component, because that's the one in the box, and it's the 0 map on the second component, because that one came from this one right here, and so that one just gets sent to x. Versus if I take a look at this direction, now on the first component, the one that's boxed, that is the 0 map, so x gets mapped to 0. And my circled one, the second component, that one is the identity map, so this one gets mapped to y. And it turns out that that's the only type of diagrams you can have, is either these types of diagrams where you either have 0 or just a single copy of Z2, or if you have multiple copies of Z2, it comes by taking products of these right here. And so that means you know what is happening. Nothing very complicated is happening. Either you're projecting onto the first coordinate or you're projecting onto the second coordinate. Nothing else is happening. You're not doing x plus y. So that's kind of a very interesting theorem that one is restricted to these types of diagrams. Those are the only diagrams one will actually get. This was actually proved in a more general case by Gabriel in 1992 without even thinking about persistent homology. And actually for any Dynkin-Coxeter graph, so this is a little bit more general than these zigzag ones. But if you've got these modules right here, in this case I'm taking fields instead of Z mod 2, so this does work in more generality. So if we've got these fields, and if I think, when I say the graph, my graph now is not the graph I create from data points. My graph now is the one where I create from homologies. My homologies become my vertices. My directed edges are these things right here. And it turns out that if I take any graph where the graph is just, you know, if I start off with an unoriented graph, so I start off with this unoriented graph, whatever. So let's put in this unoriented graph here. If I now put in my arrows any way I want, so in this case, I didn't alternate between reverse, forward, reverse, forward. I did forward, forward, reverse, reverse. Then we still have Gabriel's theorem works. So if you take any nice path graph and then put the arrows any way you want, then in order to say what are the modules that describe the persistence of these things, it will be by taking, products of these things where we just have one copy of F or 0 copies of F, and then we take the product of them and get this, and that is the only way to create. So that gives us a classification on possible persistent maps for our zigzag diagrams. And this actually works for more generality. So anything that's a Dynkin-Coxeter graph, there's a few of these. So this actually does work in more generality than just in the particular case that we're looking at. There are a variety of places for which it does not work, however. So this doesn't extend to everything. But for our nice zigzag, for these, we do have this classification. And this classification is useful in that we can do intervals now. So why can I do this interval? Well, remember, I know that since my xy goes to x here and y here, then I know what's happening to x and I know what's happening to y. In particular, I know that x gets created at time 0. It still exists at time 1, but it gets killed at time 2. And so I can talk about the interval, so I can talk about the persistence. Yeah, it's a bit of a weird persistence because it goes in different directions here. So, my arrow, I pointed this when I really should be pointing this direction. My arrows are supposed to be pointing in this direction, but I can still say that x was created at time 0 and it was killed at time 2, and so I can still talk about these intervals. Similarly, if I take a look at y, well, y goes to here, it goes there, here it goes to 0, and so eventually y gets killed off. So it was created at time 1, but then it got killed at time 4, and so we can talk about y's persistence as well. Yeah, the arrows are a bit funny between time 1 and, between time 1 and time 4, but so what, we can still talk about when y exists. And so that still can tell us things in terms of the applications, in terms of if these were witness complexes, the fact that y exists, in both here and here can give us some useful information. The fact that x gets killed off pretty easily, gives us something about, x. So if these are witness complexes or time series, it still tells you how y lives with respect to the time series, or with respect to the witness complex, or with respect to the k-density function. So even if the arrows are a bit weird, it still tells us how this generator lives within your various different choices of either time, k-density, or witness complex. So any questions about that? So how to calculate? Well, the easiest way to calculate anything, is to use software. So software will calculate zigzag persistence, as what Dionysius will calculate it. And so today we will talk about downloading and installing Dionysius for the Mac. If you have questions for the Linux, email me. I should be able to answer those. If you have questions on the PC, you're going to have to wait for me to buy a new one because my old one was too bad for me to even bring to stuff. You can still email me and I will look into it.
but I don't know how easy it is to install Dionysus on a PC, on a Windows machine. Sorry about that. But for Mac and Linux, it should work fairly well. So we just click on Get, Build, and Install. So that's pretty straightforward. That part is. It gets more interesting as we go on. Then he says on the Get, Build, and Install page, if you go down slightly, it says the easiest way is to use Mercurial. So I read the words easiest way, so that meant I downloaded Mercurial. There are, however, other ways of downloading these things as well, but I went ahead and downloaded the Mercurial. So I went to the Mercurial site, which was by just clicking on, so just clicking on the Mercurial link will take you down to here. You can then click on the download now, and that got it. So getting Mercurial was quite easy, and then I went back and followed these directions here to go ahead and install Dionysus using HG, that's the Mercurial thing, and then CD'd into Dionysus in order to basically update it. So went ahead and once I got Mercurial, then I could install Dionysus using Mercurial, and this is a Mercurial command. And then I changed directories into DCs and updated things. And I went ahead and just did this following all the directions, assuming everything would be nice. But then I thought later, well, you know, it doesn't hurt to actually know what you're doing. So then I read the man page to see, you know, what it was that this thing is. So if you are ever not sure of whether you should do these Linux commands, or I'm doing Linux type commands on my Mac. So this is all in a terminal window on my Mac. So I typed man-hc to see what I was actually doing, and this goes on for a long, long time. One thing to note is the manual pages, however, were written for people who do know something, but if you try reading things, eventually they will start to make sense, even if you're not familiar with it. But one important thing to note, if you've never used man, is you can always type Q to quit, and that will open it up again. So type this Q here, otherwise your window will be filled up with this man page, and you can use your arrow keys to scroll up and down on these things, or hit return to see more and more stuff. I also could have Googled these commands as well and gotten maybe more readable stuff too about what these things meant. Okay. There is a reason to actually know what you're doing sometimes. So I was installing these things. I didn't have much time, so I thought, let me just see if I can do a quick install and hope for the best. And so I did make a tiny little error, CMake. You know, I wanted to be able to compile, you know, C files, you know, which I often do with a make command. So I just assumed CMake was a compiler. I didn't read before I downloaded it. It's not a C compiler. So if you do not have a C compiler on your Mac, you will need first, before you download these, you should probably download a C compiler first. I downloaded these first, and that seems to be okay. But one has to have a C compiler, or it will not. You know, you can't compile without a C compiler. So MacPorts was recommended, so I went ahead and went to MacPorts, clicked the download. That wasn't bad. That got me to the installing. So you can also click on the installing thing. That got me to this page. So in this case, I had to click a few times to download. I have Mountain Lion, so I went ahead and clicked on Mountain Lion. Oh, but this time I read what I was doing. So, but first, before I did that, or no, I think actually, yeah, so still on this install page, so I should switch these two slides. I think I'll switch them before posting them, is in order to install Mac ports, yeah, so we wanted Dionysus. So for Dionysus, we needed 2 programs. For those 2 programs, we need Mac ports and another thing. So it's a bit of downloading. So if it is a big downloading, we do need Xcode in order for Mac ports to work. So we can go to the App Store. So just go to the App Store. It is a free app, and you can download Xcode. Right now, it's Xcode 5. I did launch Xcode, but it did not actually accept me. It did not actually require me to accept any licenses. So now I think the licenses are when you're installing the app. It used to be that you'd have to accept the licenses twice. So this step no longer seems to be needed. So I don't think you need 3. But if you have problems, just launch Xcode to make sure it works, and then that'll be fine. So launching Xcode, but you don't need to do this thing here anymore. But you do need the developer tools, but that's not bad. Just go to the App Store and download the free app. One also needs the command line developer tools. There's a couple of different ways to do that. You can launch your Xcode, go to Preferences, and then on your downloads, you can install your command line tutorial. But that requires that I put a link into my Apple ID into Xcode, and I didn't really want to do that. So I instead went straight to the developer page instead. When you get to the developer page, it might look like you need to be an actual Apple developer, which costs $100 a year about. You do not need to do that. You just need your free Apple ID, so just log in with your free Apple ID. You do not need to be a developer to go ahead and, so I went into here, logged in with my free Apple ID. I then did a search for command line. That gave me a bunch of things. I just went ahead and downloaded the most recent. And all these downloads, once it downloads, I double click on these things and follow the instructions, and that was true for the other things. Any questions on there? So it got me packaged, that double clicked, and that installed it. We can now install the CMake. So if you go back to the Dionysus page, it has the links, but the link is also here. I clicked on the download. That gave me a variety of different things. I clicked on, you only need 1. Since I had a fast connection, I clicked on this first one. If you have a slower connection, you might prefer something that is, tarred up, that's compressed. But I had a fast connection, so this first one worked fine with me, and then I could just double click on it. So lots of different, so this works on a variety of different platforms. One then can download Boost. So I just clicked on Get Boost or clicked on Download. Either should work. And that gave me this, to which I clicked on Download right here. So clicked on this Download right there. And that gave me that took me to the SourceForge. So you could just go straight to the SourceForge. There is another way to download Boost, but on occasion there can be issues with it agreeing with other programs, and so I went ahead and downloaded it from the SourceForge net. And I went ahead and clicked on one of these 2. It doesn't matter which one. I think I clicked on the first. And that gave me this page, to which I could just ignore this page, because you will note that while your download is processing, you would get to please take a moment to check out an ad. So this is an ad, so you could ignore that. It's just downloading. Once it's downloaded, double click and install. And so then you have your boost, and you can start doing this. There is one more step, but we've run out of time. It's a short step, though, and that is we need to make sure CMake knows where to look for the boost libraries. So boost is just a set of libraries. We need to have pointers to point towards the libraries. We'll mention that next time. So any questions about any of this? So on Friday, we will hopefully run Dionyses to calculate a variety of different types of persistent homology. Questions? Then I will see you Friday.